As you can see here, now we're gonna undo or unwind. Unwind would be a good synonym here. Unwind our proteins. So far all day on proteins, we've been working on how to coil them up into these nice hemoglobin shapes or nice myoglobin shapes. But now we're gonna talk about, let's break those apart, okay? Which is what we wanna do, for example, if we are digesting our food. So if we want to digest our protein, we're going to want to chop it back up into amino acids so we can rebuild it into a new hemoglobin or a new myoglobin or a new collagen, whatever we want to use it for. So when you eat protein, the first thing that's going to happen is a hydrolysis reaction. So we've done these before. It just looks a little bit bigger and messier now. This is what's called a dipeptide. And first of all, we've been working on all of our amino acids as you would find them in nature, which is in that Zwitter ion form. So this H wouldn't actually be here. This would be deprotonated, and this wouldn't be 2, but this would be 3 hydrogens over here, because that H would have moved over here. So just to adjust that structure so it fits with what we've been working with. So hydrolysis, remember, we add water. We would have some type of protease enzyme, something to break proteins up. And if we're gonna do a hydrolysis, then we need to find that amide bond, just like we did in chapter 13. And we're going to splice that right in half. So I'm gonna cut this right down the middle. If you remember, then we took our water, and the OH always adds where the carbonyl is, and the H adds on the other side. We're gonna have one little twist again because we have these charges here. So if we have charges in our reactants, we will need to make sure that those same charges show up in the products. So as I move over here to the products, then there's gonna be a lot of copying and pasting, and I usually work through the backbone first and then do the side chains. These are the side chains here second. All right, so looking here, this is gonna be H3N, CH, carbonyl, and then CH, OH, CH3. I'm gonna put that O here, but I'm actually gonna leave the H off, and I'm gonna send the H over to the other side. And then a separate molecule here, don't forget the positive, would be NH, but now I've gained not one H, but actually 2 H's to make it protonated. And then I'm just gonna copy carefully for the rest of it. CH, CH3, CH3, and then COO minus. And so you can see on my products over here, I have Zwitter ion form of both of my products, and that was just moving one of those H's over here so that I have 2 H's instead of the one that I would have done before. If this was 3-anyl valine, then this is now 3-onine and valine all by themselves. So that would be digesting our protein. And if you can imagine that this black little piece of ribbon here is a protein, digestion is going to take it and it's going to cut and cut and cut off those amino acids. So that would be, digestion would be to cut it into small pieces. Now, in contrast, another way to undo our proteins, this was actually not unwinding, this was actually breaking them apart. Denaturation is a little bit more gentle. And if you've ever, say, curled your hair or cooked meat or eggs or nuts or something like that, or eaten yogurt, you've actually interacted with denaturation before. So denaturation is going to alter the shape of a protein. And in doing so, it's probably going to affect the texture and the water solubility too. So it's not just going to alter the shape, but also the texture and the water solubility. Denaturation is going to be unfolding or unwinding our secondary, our tertiary, and our quaternary structure. And it's usually irreversible. So there's a little picture here. I have this folded up ribbon, and to denature it, here's some ways we can denature it. Is going to unwind it, and crucially, when you unwind it even just a little bit, you're going to lose most of your biological activity, or all of it. It won't be able to work as a catalyst anymore or whatever. Sometimes you can renature. Maybe if it's just a mild unfolding, you might be able to redo it, but usually you can't. Usually we're just going to go this direction. So to give you a visual of this, this is gentler. If this is my protein and it's all folded up, this is denaturation. I'm just unwinding it. So not hydrolysis where I chop it up, but just unwinding it. So I still have the primary structure, or that straight bit, present. So let's look at a few different agents that can denature a protein. And again, you've interacted with some of these before, just maybe not thought of it. So this denaturing is going to be gentle enough that it's going to affect or undo my intermolecular forces. And so that's what we had seen in this secondary, tertiary, and quaternary structure, was intermolecular forces. The first one we'll look at is if you change the pH, then you can start to force your protein to unwind. And here's the problem. If you change the pH, then you affect your electrostatic attractions. The electrostatic attractions were attractions like this back on slide 3, where I had a positive and a negative. So let's just say I flood this with hydrogen all of a sudden. I lower the pH. Then this H is going to get added on to the oxygen right here. And suddenly I don't have a positive and negative, I have a positive and polar. Still an attraction, but it's going to weaken this. And where this might have been really tight before, now it just loosens a little bit because the attraction is weaker, and that starts to unfold the protein and reduce its function. So this would be if I lowered the pH, this attraction would become weaker. So electrostatic attractions are affected by a change in pH. Remember, electrostatic attractions were between acids and bases, so they're going to feel the impact of a pH change the most. Examples of this would be if you have an acid burn on your skin or your eyes or some kind of tissue that's made out of protein. That protein unwinds and you change the texture, right? If you have a burn, then the skin gets harder because the proteins have unwound. Another place less awful than that would be when you have acid in yogurt or in milk. The acid in milk causes the proteins in milk to unwind, and you get yogurt, which has a different texture and different water solubility than your milk. And that's because the acid that the bacteria produced caused some of the proteins to unwind or to denature. So that's changing pH. Next one down, we know that we watch out for heavy metals, not as in music, but as in chemistry, right? And a couple of ones we watch out for are silver and mercury and lead. So silver, mercury, and lead. These will mostly disrupt my disulfide bridges. And so where I might have a nice bridge like this before, after I add these metals, then the sulfur actually prefers to bond to maybe the lead instead, and so I get these ionic bonds instead of the disulfide bridge. This was used, not so much anymore, we try to avoid those now, but a couple hundred years ago, when they would make hats out of wool, they wanted the wool to change texture and be able to straighten out a bit, so to unwind wool, they would use mercury, and hatters, people that made hats, would use this mercury a lot, and so that was probably where the term Mad Hatter came from, because people who made hats ended up exposed to mercury, and that in turn disrupted some of the proteins in their body, in their brain in particular. So heavy metals will cause your proteins to unwind. Next one down, if you shake or mix, that's a way to add energy to a protein, and if you add energy you can overcome some of these attractions. So shaking or mixing, this is especially going to affect your polar and your nonpolar attractions. And an example of this would be if you beat egg whites. If you've never tried this, Google it or do it in your kitchen. If you beat egg whites for maybe 5 minutes or so, they get really stiff and white, kind of like an egg gets when you cook it, where it gets stiff and white. And again, changing the texture and the shape is a hint that you denatured the protein. So egg whites are protein, and when you beat them, then those proteins in the egg whites unwind, and they actually re-stick to each other and become stiff in a new sort of shape. So shaking or mixing can denature proteins. A final one would be gentle heat, and I'm calling it gentle instead of strong because strong heat would actually break all of your bonds. This would be, for example, if you burn something, like if you burn hair, you know that it smells wrong, right? Or you burn meat, it smells different, tastes different. So gentle heat would be something like if you cook eggs or cook meat, or with your hair, if you heat hair, or something they'll do to seal up blood vessels after surgery is called cauterizing. They take a hot little piece of metal and they basically close up your blood vessels for you by denaturing the proteins in them. So gentle heat will especially affect polar and non-polar bonds. And if you can remember that these are weak attractions, if you just heat them up a little bit, you're essentially going to melt all these attractions. And so if you can imagine back to this page, if I just add some heat to all of these, you kind of melt it and you could straighten your hair out temporarily, then it'll go back to its shape. With meat and eggs, you can't so much undo it and then have it reform, but with meat, you would stretch these proteins out. And that's one reason why meat gets kind of tough as you cook it for too long, is all those proteins get really straight and you lose that water that's trapped inside of this structure also here. So those are some ways to denature or unwind your protein into just a nice straight piece. And then also you need to be able to do this hydrolysis reaction where we break or digest that peptide bond. So this is going to take more energy, this is going to take less, but both are disruptive or helpful in their own ways.